Good evening, everyone. I'm Carmi Garzione, the Dean of the College of Science, and I just want to thank you for joining us again for the third lecture of the 2026 College of Science Lecture Series. Before we begin tonight, please join me in giving tonight's musician, Britt Warner, another big round of applause. I also just want to highlight that this week is Space Week. That's a space-themed week with lots of events and activities centered on the celebration of space sciences. You saw a video last week that featured some of our space scientists, and outside you may have picked up trading cards. So some of these scientists are in the audience. There were 3 of them, so look through your trading cards. If you spot a scientist, go get an autograph for your space-themed cards. And if you didn't get your cards, please feel free to pick them up after the lecture. We are now at the midway point of the 2026 lecture series, and in case you couldn't join us for the first 2 lectures, we've had a terrific set of talks from George Sutphin on aging and Dr. Martha Bhattacharya on the study of fruit flies to learn about human diseases, particularly neurological diseases. Those lectures are available on our YouTube channel, and if you would like, you can always check them out or share them with other friends. And it's great again to see so many of you in the audience tonight for the continuation of this week's lecture. I'd like to take a moment to recognize those in the audience that are part of our Galileo Circle. These members are a community of individuals whose support is vital to the College of Science. Thank you for your continued support of our students, our faculty, and our staff, and for being here with us tonight. And I'd like to thank Arizona Arts Live for their continued partnership with the lecture series and for helping us bring this lecture series to life here in Centennial Hall. I'd also like to thank our partners for the lecture series, in particular our presenting series sponsors, the Marshall Foundation and the Research Corporation for Science Advancement. And our series sponsors, Holualoa Companies, O'Reilly Chevrolet, South 32, Tech Launch Arizona, Tucson Electric Power, TMC Health, and Visit Tucson. We are deeply grateful for your support. Thanks. And I'm always happy to share that we continue our partnership with the University of Arizona Poetry Center for this year's lecture series, and in the spirit of reaching broad audiences through diverse platforms for communication, a poet will read their original work, which is somehow connected with the theme of tonight's lecture topic. And so tonight's poet is Sarah Sams, an assistant professor of English at the University of Arizona, where she teaches undergraduate and graduate courses in creative writing. Her book of poems called Atom City was published in 2021, and the book explores Oak Ridge, Tennessee, the secret city built by the US government to house the Manhattan Project. We are delighted to have her here with us tonight. Please join me in welcoming Sarah to the stage.
If I could read the atom like a poem, I would take each trait to task, all my ailments back to the aisles they came from. Would I also ask Vane to serve as guarantor? Unraveled, my arteries lap the earth twice. She just can't be quoted. When I try, syllables soften. I'm stuck between the stage and the audience. How long until I mention the home of a secret code, the bombs? I bring a personal, historical lens. No, not me. Always me. I want this to be a thing we do together. Mend the story. But what story was there before the story was written? I can almost see thought, as if thought were on the edge of matter, and matter, the particular fear I'm gearing up to face. Thank you.
Thank you, Sarah, for that thought-provoking poem, which does set the stage for tonight's talk. And I'd like to now introduce tonight's featured speaker, Dr. Lise-Marie Imbert-Gerard, who is an associate professor in the Department of Mathematics at the University of Arizona. Lise-Marie grew up in a small town in southern France and went on to study mathematics at the École Normale Supérieure de Cachan. She then earned her PhD from the University Pierre and Marie Curie in 2013 and was a postdoctoral researcher at the prestigious Courant Institution of Mathematical Sciences in New York. Lise-Marie is the recipient of a Kavli Fellowship given by the National Academy of Sciences and awarded to future leaders in US science, a Leslie Fox Prize from the British Institute of Mathematics and its applications, recognizing the best young numerical analysts, as well as a Department of Energy Early Career Award, recognizing exceptional promise and potential impact. Her research is also supported by the National Science Foundation and the Simons Foundation. Dr. Imbert-Gerard's work is driven by applications and aims at improving our understanding of the physics of complex media. Amongst other things, she develops efficient mathematical algorithms that help scientists undertake large-scale simulations of wave propagation in fusion reactors. Tonight, she will tell us about how the role of mathematics is shaping the future of these reactors. Please join me in welcoming Dr. Lise-Marie Imbert-Gerard.
Good evening, and thank you for being here tonight. I am absolutely delighted to be here to tell you about fusion science, but more precisely about how mathematics helps shape the future of energy. So as an introduction, I want to tell you that there is there's a pressing need for investment in energy, not just to supply an ever-growing demand at the global level, but also to improve the standard of living for everyone, everywhere. And before I go anywhere near this, I want to ask you, what do you see here? An equal sign. Yes, I am a mathematician. I'm going to be telling you about a mathematical point of view on this story. And I want to start by telling you that equations in mathematics are often used as a scale where what's on the left is balancing what's on the right. Now, equations can represent complex phenomena that are happening in the physical world, and we can gain a lot of understanding about these problems thanks to equations. Now, if you remember the famous quadratic equation, you think that maybe it's always easy to find solutions to equations. The fact is that is not true. And most of the time, it is very hard to find solutions to equations, especially when the problems that you're looking at are very complex. However, from the equations, we can gain a lot of understanding about the problems by analyzing these equations. And there's another aspect of applied mathematics is that we can also gain a lot of understanding about physical problems by simulating what is happening in the physical problem. And this is done through mathematical techniques that are going to build approximate solutions to these equations. Now, just to say a few words about the complex media that Carmi just mentioned, I want to give you one example. In my work, I study how noise propagates around planes, because noise reduction would be nice. If you live in Tucson, you know that. And the complex medium here in which the noise is propagating is the air that is around the plane. So if you think of the air that is just coming out of an engine of a plane, this can be really hot, but the air that is further from the plane is very cold. And the noise is propagating in very hot air, in very cold air, and in transitions in between. This is the type of complex media that I'm interested in. Now, enough about just mathematics, and let's now talk about mathematics for the problem of tonight. So wouldn't it be nice if we could use some inspiration from the stars that are shining bright in the sky to bring light into your homes? I think that would be spectacular. So among all the stars, the sun is at the center of our solar system, and it is the primary source of energy on Earth. Without the sun, there would be no plants, there would be no food, and there would be no us. So that is inspiring, and maybe we can use that to solve a big problem. So why should you care? You are consumers, and you might care what is the product that this might bring to you. Well, ideally, we can get inspiration from the stars and bring power on the electric grid all the way to your homes. But this is only possible if we start at the bottom by understanding what is the power of the stars. This is the basic idea. And we build up on this basic idea by developing and refining the idea to get to bringing power to the grid for you. So you can think about it as there's two different phases in this development. There's the basic science part and the product development. We are here in this lecture series to talk about basic science. So this is what I'm going to focus on. So what is it that is happening in the sun? What is it that powers the sun? Well, these are fusion reactions. Nuclear fusion are particular reactions. They look a little bit like chemical reactions, if you remember, if you've ever studied that in school, in that there's what you start from on the left, and it recombines in what you get on the right. So here we have one example of a fusion reaction, and this is the most studied reaction in experiments. So on the left, we have two nuclei. They have positive charges, and then they come together to fuse, and what comes out is another nucleus, that is bigger, that is fusion. You take two lighter things and you bring them together to build something bigger, and then there's a neutron that is released. But the thing that is really fundamental, and that is the reason why it makes sense to study fusion reactions in our program to bring fusion energy to the grid, is that if you were able to measure the mass of what you start from and the mass of what you end with, you would see that it's heavier when you start than when you end. So where did the mass go? Well, E is equal to mc squared. It was released under the form of energy. And this energy is really very vast amounts of energy, and this is why it makes sense to study this. So the next question that you might ask me is, okay, this is a great idea, good. Maybe you trust me on this one. But how hard is it? Well, it turns out it is actually very hard. So the nuclei, they're bound together, all of these little pieces, they're bound together by a very strong force. So you could wonder, well, what if I just bring them together? Are they just going to stick together? Well, the answer is yes, but good luck to get them to get close to each other, sorry. So there is a competing force. This force that binds the nuclei together, it is a very strong force, but it only works on a very short distance. So they already need to be very close to each other in order for this to take action. Now, bringing them together is very hard because nuclei have positive electric charges, and positive charges repel each other. So think about it this way. If you were to have two nuclei and you would like them to fuse, you would have to do something like pushing them all the way up this very steep mountain, and only if you were able to bring them all the way to the top there, they would finally feel this attraction force, and they would bind together and fall in this well. Once they're there, they stick together. But it is very hard to bring them there. And so Can we really do it? Well, the answer is yes, it can be done, but it requires some very extreme conditions, and in particular, very high temperatures, because particles, if they are very hot, they have a lot of energy, and they can actually make their way all the way up this mountain to meet each other. Okay, so we need very high temperatures, but what happens when we have very high temperatures? Here I need to tell you a little bit about the states of matter. So you are very much used to sitting on a solid, drinking a liquid, and breathing air. But under these very high temperatures, the matter is not in any of these forms. It is under what is called the fourth state of matter, and this is called a plasma. Now, we're not very used to it on Earth, but out there in the solar system, it turns out that more than 99% of everything in the solar system is under the form of a plasma. So it exists, we know it's out there, we are simply not very used to it on Earth. Now, not all plasmas are very hot, but for fusion, we need very hot plasmas. Now, what is particular about a plasma is fairly similar to a gas in that the particles, they're moving around and always trying to escape. They always want to push away from each other. So if we want a fusion plasma, we need it to be very hot. And the next question that you should wonder is, if it is going to be this hot and particles are just going to be trying to escape all the time, how could we keep it together? That is a very important question, and this is what's going to be the focus of pretty much the rest of the talk. So how do we keep it together? I want to ask you to think about a very simple question. The sun is powered by fusion reactions. How does the sun keep it together? It is made of plasma, so particles would like to run away. Why is it that they don't? And that the sun has been out there for a long time, heating us up, and fusion has been occurring like this. Do you have any idea? Gravity, exactly. The gravitational force is absolutely spectacular on the sun. The mass of the sun is approximately more than 300,000 times the mass of Earth. And if you want to compare, to have an image in your head, it would be like comparing the weight of an elephant with the weight of a 7-day-old baby mouse. Okay, so the sun can do it. We cannot do this on Earth. So, keeping it together, in technical terms, we call that confinement. The plasma is a wild beast that just wants to run away, and what we want to do is to keep it together to confine it. So the question that I want to try to answer with you tonight is, how do we bottle up? What can we use to hold it together, to confine this plasma? Now, in the framework of this program that we described earlier, I can now tell you a little bit more about the steps of this program. So we want to start from the idea of fusion experiments. What is it that we can do to reproduce what's happening out there in the sun? And then ideally, what we would like to be able to do is to control these reactions. So not only to keep it together, but control the reactions. Because what we really want to do is to produce reliably some energy that can be then put on the grid. So this is the program that we would like to follow, but what we are focusing on here tonight is the basic idea of fusion experiments. And this is what I want to tell you about tonight. So you might ask, from yesterday to today and tomorrow, what is the state of fusion experiments right now? There has been about a century of research on fusion reactions, so that's a long time. But fusion is really hard, as you know by now, so we are not just here yet. This is a map that is showing you around the world where are current experiments. Not just experiments, fusion experiments that are running now, that are operating, but also some that are under construction, and even more so that are planned. So this is a very active field of research, and it's very exciting to be working in this field. And before I go on to tell you a little bit more about the history of fusion, I want to point out one little detail that you can see on the slide here. There is a lot of public investment in research facilities, but in the past few years, there's been a lot more private investment as well. And this is great because there's a lot of different ideas to confine the plasma and a lot of different concepts that are used for fusion experiments. And we're learning a lot. So this is really complementary strengths that we're building to understand better fusion reactions. And the fact that the private sector is investing kind of brings a different point of view on the research. So public research allows for very large collaborations, and they can build some very big experiments. The private sector is interested in a different aspect, and sometimes they try to develop things at a different scale. So maybe things that are smaller, that might be easier to develop for infrastructure. So it's really complementary strengths that are coming from all sides. Now let me tell you a tiny bit about history. There's a lot to say, but I just want to mention a few milestones. So in '68, after about 20 years of study of experiments, is the first time that there was a big breakthrough in confinement. 20 years. That tells you that it was hard to achieve, right? Okay. In 1991 is the first time that there was a controlled release of fusion energy. So before that, we were able to confine plasmas, we were able to have fusion reactions, but not necessarily to control the release of energy. And now you might have heard more recently, in 2022, there was a big milestone that was reached in California. And that was the first time that all the energy that were put in holding the plasma and in having these fusion reactions occur was outweighed by the output of energy. So more energy came out of the experiment than what went in. It was the first time in 2022. Okay, now even more recently, you might or might not have heard, but in 2025, there was a new milestone in terms of long-time performance of a fusion experiment. Now let me tell you that there's three things that are really important for this kind of experiments. The temperature, as we said before. The density is another one, because if you want, so the particles, if they're going real fast, they can meet each other. But if there's not enough of them, they're simply never going to cross each other. So density is another thing that is really important. And the third one is precisely the time, the confinement time. So we need for this to happen over a long period of time so that we can extract more and more energy. So these are all frontiers in research of fusion experiments. And I just want to mention that the color code here, the three colors that you see for the milestones, yellow, orange, and red, represent the three main types of experiments. And the red one is the Stellarator, which we will focus on tonight. But the green color represents a whole bunch of other concepts. So there's really a lot of ideas that are developed out there. And before I go any further, I just want to repeat and say it very clearly that fusion energy is a very promising source of energy that would be abundant, that would be safe, and that would be clean. So you should care about how the developments are going. So now that we've talked in general about experiments, I want to get into more precisely these stellarators. So I don't assume that anybody knows anything about stellarators, but very shortly, hopefully you will. So the basic idea of stellarators is to use a magnetic field to confine the plasma. So remember, the plasma is wild. We need to confine it. We need to keep it together. It turns out that the action of magnetic field can confine plasma particles because the plasma particles are charged. So this is an excellent excuse for me to tell you a little bit more about mathematical modeling in this context. I'm going to have to tell you a little bit about plasma modeling and a little bit about electromagnetic modeling. So let's start with plasma modeling. Plasma modeling is very hard. A plasma is something that is very complicated, and modeling it from the mathematical point of view is very hard. Why? Because in a plasma, there are things that are happening at a very small scale, like the interaction of particles, and then the size of the plasma itself has to be big enough. Think about comparing the size of a dime with the size of a football field. Well, if you want to see both at the same time, it is challenging. And in the same way, if you want to model mathematically a plasma, it is very hard. So let me just start from what do we know about a plasma? A plasma is made of particles. Okay? So think about individual particles. There are mathematical models that are based on individual particles, and just ask the question, if I have one charged particle, what's going to happen to it? We're going to play with that in just a moment. But of course, you're going to tell me a plasma is not a single particle. By the way, if it was a single particle, you could run a long time before you got fusion out of that, right? Okay, so you actually have, ideally, plenty of particles that are moving around. And because they are behaving a little bit like a gas, there's mathematical models that have been developed for the description of gas that can be used to describe the plasma if you want to know a little bit more than just looking at a single particle. Now, a plasma also, so the thing that is characteristic in a gas is that these particles, they're moving around under their energy is pulling them around, and then they collide with each other. So this is typical behavior in a gas. Now, if you look at it from a little bit further, a plasma also has some collective behavior. So the particles are not just doing what they want on their own. And so this is similar to what would be a fluid behavior, where the fluid is moving, the particles of fluid are moving together. So there's also mathematical models that rely on fluid models to describe a plasma. So all of this is very hard, and here I just need to take a little break and to tell you one thing. As a mathematician, the kind of problems that come out of modeling a plasma, a fusion plasma, is just amazing. And I try often to talk to more mathematicians about it, because I would really like to see more input of mathematicians on the study of plasmas. So we talked about plasmas. Again, it is hard to model them. And now finding solutions to these problems is very hard, and that definitely requires some numerical simulations and a lot of understanding of what is happening to be smart about the numerical simulations. Now let's talk a tiny bit about electromagnetism. I guess that some of you, maybe most of you, have played with some similar experiments, just playing with a magnet or playing with a basic concept of an electric engine. But I just want to remind you that electromagnetism is everywhere. It is everywhere in nature. Light is an electromagnetic wave. But also, it is everywhere in technology. So let me ask you a few questions. Let's see. Who among you took the Sunlink to come here tonight? Can you raise your hands? A few. OK, not a lot of you. How many of you got maybe an X-ray or an MRI recently? Some people, OK. And now, with this one, I know I'm going to win. How many of you have a cell phone in their pockets? OK, so electromagnetic fields are everywhere in applications that go from medical imaging to telecommunication to transport. So they're really everywhere in technology. And I'm going to tell you about mathematical modeling for electromagnetism. Before I click onto the next slide, I just want to ask you to take a deep breath. OK, here we go. So I don't know if you are stunned, but you should be. So these are Maxwell's equations, and there's something very particular about them, is that they actually are an excellent mathematical model, and they represent what's happening to electric and magnetic fields at all possible scales. I just told you that for plasmas, it is really hard to look at all of these scales from a modeling point of view. Well, here, for electromagnetism, it is the opposite. This model is spectacular. It knows it all. OK, so I'm not going to spend too much time on this slide, but I just want to tell you a little bit more about magnetic fields, because this is really central to our idea of building a magnetic bottle to confine the plasma. So this is, again, a representation or an illustration of what the magnetic field created by a magnet is. But I just want to tell you that there's two types of representations that I'm going to use in what follows. One of them is to represent a magnetic field with little arrows. Sorry. So arrows have two properties that are really important. One is the direction. It tells you where to go. And the other one is the length. It tells you how strong is the magnetic field. This is one way in which you can represent magnetic fields. Now, the other way would be, what if I sit anywhere and I try to follow these little arrows one after the other one? That would trace out what are called magnetic field lines that are represented here on the right. Now, for the following discussion, I'm going to be using magnetic field lines. So finally, we've talked a little bit about mathematical modeling, and now I want to take you with me on the path to define the concept of a stellarator. We're going to see this thing taking shape in front of our eyes. And for that, we're going to use an individual particle model to describe how a charged particle is impacted by a magnetic field. So let's get started with the simplest possible magnetic field. I'm representing here a magnetic field with its field lines. So these red lines are representing what the magnetic field would be. And the question is, how would a charged particle move in there? Well, this is the mathematical model that represents this, and that describes how the velocity is going to be affected by what is called the Lorentz force, which is the magnetic field acting on the particle. Now, you are very lucky tonight, because this is a mathematical model whose answer we know exactly. There's actually a formula. I'm going to spare you the formula, but we know exactly how the particle is going to move here. And this is how the particle is going to move. It's going to have a fast rotating motion that is going to keep it close to a magnetic field line. But, okay, so this, let me stop right here. This is the basic idea of magnetic confinement. Because when you have a magnetic field and you have a charged particle, the magnetic field is going to be somehow stuck around the magnetic field line. Okay, so this is a good idea because we're kind of getting close, but see what's happening? The particle, its average motion, which is represented here in blue at the center, it's actually moving along the field line. And there's absolutely nothing the field can do about this. The motion along the field line is free. So the particle is escaping at the top. Do we like that? No, we don't. We want to keep it together. Okay, so let me ask you one question, and you can take a few seconds to think about it. I have these magnetic field lines, and I don't like my particles to escape neither at the top nor at the bottom. So what could I do to this magnetic field? This is not a perfect magnetic field for confinement, but I could do something about it. How could I change my magnetic field so that I would avoid this problem? Any ideas? Yes, a circle, excellent. So how about you grab it, you wrap it up, and you make it a circle. That is a great idea. So close it up is what I would recommend. And to give you an idea of how that would look like, I don't know if all of you are hungry just yet, but we could put all of these magnetic fields together on a donut surface, and that might be a much better way to confine our particles. Now, before I go any further, 2 points right here. Number one, this is one idea to use magnetic fields. There's many other concepts that use magnetic fields and that also achieve confinement. The second thing is that this is a perfect time to advertise a little bit more mathematics right here. There's an entire field of mathematics that is called topology, and that loves talking about shapes. Okay, so this is a particular shape, and can I ask you what you think is spectacular about this shape, except the fact that it's delicious? It has a hole, exactly. Do we have mathematicians in the room, maybe? Okay, so having a hole is something that is very fundamental. It's, again, gaining insight from the mathematical point of view about a very abstract property. There is a hole in this surface, and that matters a lot for a whole lot of properties of this surface. So I will get back to this a little bit later. So the next question, of course, is, can we look at particles in such a field? And are they confined? That would be amazing. Okay, so this is a little bit of a better field, and we can ask the question, what is the mathematical model for particles moving in this field? Now, just because the magnetic field has a shape that is different, we now have a model that doesn't look much different, but we do not know the solution to that model. Okay, so this is not great because we cannot know exactly what particles can do, but fear not, mathematicians are not going to be dismissed so easily. Okay, so we cannot describe exactly the particle of a motion, the motion of a particle in such a field, but you remember this idea of average trajectory that I introduced earlier, the blue trajectory that was explaining what the particle was doing aside from the fast rotation? Well, there are some very strong mathematical tools that allow you to use to describe the average motion of particles for this problem, and we know how to study this. And the one thing that these tools tell us is that there is a force that is going to act on the average particle, and that is going to make the particle move across magnetic field lines. So the particles will still escape. Okay, so was it still such a good idea? Well, particles are trying to escape, but again, there is a solution to this problem. And the solution is to wrap up the magnetic field lines. I want to give you an idea of why is it that we can do this. And in order to do so, I'm going to use an analogy here. I want you to think about a honey dipper. You might or might not have used a honey dipper, but as you can see on the video here, the honey is trying to escape because there's a force that is pushing it away, again, gravity. But if you twist the honey dipper, you can bring the honey back and it can stay around the honey dipper. Now, how does that compare to what we're trying to do? This is a very simple schematic representation of what's happening. You have the gravity force that is pushing down, all the honey is pushed down, but the honey that is in the blue part is pushed outside of the honey dipper. Okay, so if you think of my donut shape and how the particles move around there, there is a force that is pushing them to escape away from the donut surface, and again, the particles that would be on the blue part here, they would be pushed outside the surface. Okay, so what can we do about this? Everything that is red here is pushed inside, and everything that is blue is pushed outside. So we can use the idea of twisting that we get from the honey dipper to do the same thing and twist our magnetic field lines along the donut surface. What is the gain in this case? Well, particles, sometimes they're going to be on the outside of the magnetic field line, and they're going to be pushed away from the surface and outside, but then when they continue moving more or less along the magnetic field lines, they're going to find themselves inside the donut, and there the force is going to push them back towards the surface. So on average, particles are going to remain close to the surface, and that is the key to a concept that is called toroidal confinement, because a torus is the name of this shape, the technical name. Okay, so now we have a great idea about confinement. Now, two more little twists to this story. What do I need to do to have a stellarator from here? I am almost there, but not quite yet. The thing that is fundamental about the surface is that it has a hole. And then the magnetic field lines, they need to twist around it. Well, a stellarator is not just a simple donut like this, it's actually a wiggly donut. So it still has a hole, okay, from the topological point of view. It still has this important property, but you can allow it to move around. When you go the long way around the torus, you have this shape that can change. This is the concept of a stellarator. And again, particles remain close to the surface on average. So here's my second little twist here. Think about it as, it's not that I just want one surface, but what would be really cool is if I can have several of these surfaces nested inside each other, so that particles would remain to many surfaces, okay? So this is the concept of stellarators. We have a shape. It's a wiggly donut. This is our shape. So what I want to tell you next is, this is a concept. How do you go from there to having the exact shape that you want to build an experiment out of? So now we really want to ask, what is going to be the precise shape of a magnetic field? Now again, math is coming to the rescue here, because there's a lot of possibilities, right? Once I've told you I need a wiggly donut, each one of you could give me a wiggly donut and they would all be different, right? Okay, so what do we do about it? Well, what would be really amazing is if we could say, well, I want to be able to measure confinement, the property, the quality of confinement of a surface, and I want the best possible surface that does that. That would be amazing. Well, it turns out that we cannot do exactly that, but there are some mathematical tools that are used for what is called stellarator optimization, and this is trying to find the best possible shape so that it confines well the plasma. Remember, we are trying to build a magnetic bottle to hold the plasma. So how do we do this? With mathematical techniques, there is a way not to find the perfect surface to do this, but to gradually improve surfaces by just nudging them in little places and move them just a little bit to improve them. So you have to define a criterion that says, how do we measure the fact that the confinement is of good quality? And then there are some very powerful mathematical techniques and computational techniques that do exactly this. They tell you, if you have a surface, you compute the field there, and you have a way to say how good the confinement is. Well, from this, the techniques tell you where should you push the little surface, maybe a little bit outside or a little bit inside, over here and over there, and it improves them little by little. So if you really want to have a better shape, you need to do that over and over again, and you need to repeat this computation so that you find something that is really much better. Now, this is a great idea, and the one thing that I want to emphasize before anything is that at every single step of this, you need to compute the magnetic field. So you better be smart about how you compute your magnetic field. I always tell my students when I teach numerical methods, if you have to do it once, maybe you can do it naively. If you have to do it many times, you better be smart about it. Okay, so maybe you would ask me, before I talk to you about numerical methods to compute this field faster, does this work? Well, the answer is yes. You remember this milestone that I mentioned from 2025 of long-time performance of a fusion reaction? That was in a stellarator, and that's a stellarator that has been optimized in its design. And this is exactly, what you're seeing here is precisely the magnetic bottle. This is a visualization of what is happening inside that experiment. Its little name is W7X, but what it actually is the best wiggly donut magnetic bottle in the world. I don't know you, but I find this image pretty spectacular. So you see the wiggles here? And this is just, of course, part of the experiment, and it does look like a wiggly donut going all around. But this, again, this shape has been optimized using numerical methods and mathematics to obtain better results, and it did reach some groundbreaking results just last year. So it does work, if anybody asks you. Now, I want to tell you a little bit more about how do we compute these things fast. So I was involved in a collaboration that was doing exactly this, trying to compute magnetic fields on these particular shapes where you have not only one wiggly donut, but all of these surfaces that are nested inside each other. And although I'm not going to give you too many details, I do want to give you little nuggets of how mathematicians think about things and how do they do to make it faster and to make it relevant. So we don't just want to do things fast, but we want to do things well, right? We want to make sure that the results that we're getting are reliable. So mathematical understanding behind any computation is just really key to doing it fast and doing it well. So 3 little points here. 1, mathematicians love to reformulate the problem. So think about it in this way. Maybe you have some children, or you've seen this behavior before. You have a puzzle that you need to solve. You turn it around, and you try to find from which direction is it easier to see what the problem is. This is what mathematicians do when they reformulate a problem. And in this case, in this collaboration, we did this really based on these different surfaces that were nested inside each other. So the shape really played a role. And in the other nuggets as well. The next point that I want to mention is how do you break down a problem? So now you have a big problem that might be really complicated. Maybe, ideally, you can break it down into smaller problems, and the solutions of these problems are easier to find, and they can help you put together a solution to the initial problem. And finally, when we think about numerical methods to construct some approximate solutions to the problems we're interested in, there's a very basic idea that is to approximate the solutions using many, but very simple functions. So it's the way in which you represent the solution. And here I cannot resist because I want to tell you why is it that I was very excited about this project. And it's going to be in the second nugget that I mentioned here. It's about breaking down the problem. So the magnetic field that we're trying to compute it's on these wiggly surfaces, right? And you remember that I'm interested in complex media? Well, in this case, the complex medium is exactly the shape of this thing. It is complicated. It moves around. Everywhere, it has a different shape. This is the complex medium. And the thing that I really like about this contribution is the secret structure of magnetic fields. So here I'm using magnetic fields represented with arrows, like I described earlier. And the thing that is absolutely spectacular is that magnetic fields can be decomposed. Every magnetic field can be decomposed into the sum of 3 contributions. And the 3 contributions have very different properties. These are just representations to give you an idea of these properties. So if you look at the first part on the left, you see that all the little arrows, they're escaping from the center, right? So we say that this acts like a source. There's something that is moving away from it. This is the first part of the magnetic field. Then the second part of the magnetic field that is represented here at the center, you can see that there's some motion that is going around. So there's something there's a rotation motion here. And this is what describes the second component. Now the third component, it has to do with the shape. So you see here that the arrows are, if you look at them vertically, they're pointing towards each other, but if you look at them horizontally, they're pointing away from each other. So this is a particular behavior, and this is what is called the harmonic vector. It's the harmonic component of the magnetic field. Now this component, if you were looking at a magnetic field in space here, it would not exist. But on a surface that has one hole, not only we know that there is a harmonic component, but we know exactly how complicated it's going to be. And that is very deep mathematical understanding at the service of numerical simulations. Okay, so this collaboration resulted in a code that is computing magnetic fields faster, maybe like 100 times faster than other codes. And think about 100. If I ask you a question and you need to wait 100 minutes, or I ask somebody else a question, and they give me an answer in 1 minute, you can bet who's going to be my collaborator. So computing fast is a good thing because we can investigate a lot of things. Now, what do people do with this? This code is available online, and scientists can go and use it to optimize surfaces. Now, what is it that they can do better with it? Well, what they can do better is that because everything is faster, they can now use criteria that are more and more involved, that maybe, for instance, instead of relying on a single particle motion of a plasma, they could rely on a gas description of the plasma, or maybe a fluid description of the plasma. They can take into account more complex physics to inform the optimization of the shapes. And do people do that? Oh, yes, they do. Sky is the limit here. I just want to show you 3 examples that come from 3 databases that are available online. People go and optimize surfaces by adding criteria that they think are more relevant. Are you ready? Okay. These databases have hundreds of thousands of shapes that have been optimized to design stellarators. This is what we can do now with the computational power of that is behind all of these computations. So all of this relies on deep mathematical understanding, in particular of donuts, but not just. And this is what people are looking into to inform the decision process of what are going to be the experiments of the future. How are we going to choose to define them, to design them, to shape them? So that we have a good confinement of the plasma, and we can do higher temperatures, higher densities, and longer time of confinement, so that we can create so much energy that then it goes into the power grid and into your homes. Okay, now I just want to tell you a little bit more about shaping the future of fusion energy beyond the magnetic field. So we focus here on really this idea of confinement and the magnetic field. And the plasma is so wild that you cannot do anything else. You have to focus first on confinement to choose the shape. And otherwise, you're doomed, and it will not happen. Now, there's a lot of other concepts out there, but again, in the world of stellarators, the next step when you want to design a reactor, of course, in the real world, a reactor is not just a magnetic field, right? First, you need to create this magnetic field. And this is done with magnets. So here you see a magnetic field on the left, and then one type of magnets that are described in red in the middle, and another type of magnets that are described in orange on the right. Now, here's something that used to be done. First, people would optimize the magnetic field, the shape of the magnetic field, and once they had a magnetic field that they were satisfied with, they would hand that over to people that cared about the coils, and they would say, okay, can we now look for coils that are going to create this particular magnetic field? Thanks to powerful numerical techniques now and simulation techniques, these two steps can be combined into one. So now you can explore even more different shapes of the magnetic field and the coils. And the advantage here is that if your engineering friends are telling you these shapes are way too complicated, I don't want to build them, make them easier, now you can use criteria in your optimization to penalize things that are very complicated, to try to simplify the shapes of the coils as well. Okay, so from real-world design, then the next step is to commercialization. So we've talked a lot about experiments and controlled fusion tonight. But then if we want to be able to produce energy on a reliable way, here's another place for you to think about how mathematics can also have an impact beyond the design of the reactors. If we're going to run experiments on the large scale, where it's going to be really big, there's going to be a lot of particles, and there's going to be a lot of plasma, you know plasma is not a nice player, right? You're going to have this plasma here, you're going to have an optimized field that is going to try to hold it in place, but when you switch on your fusion experiment, when you inject the fuel, and when you have these fusion reactions happening, the plasma is going to get turbulent, and is going to try to escape again. Now, here's a place that is really a dream application of mathematics, and that's real-time control of experiments. So you would have some measures of what is happening. You would be able to look at what the plasma is doing, and maybe it starts drifting a little bit away from the magnetic field. Well, having mathematical tools and simulations that tell you you need to input something a little bit there, push a little bit of energy there to push the plasma back inside the magnetic bottle. That would be spectacular, and that is the future of mathematics in fusion energy. Okay, so all the way up to ideally, in our lifetimes, seeing the power of the stars on the electric grid. Now, before I wrap up, I just want to thank the agencies that are funding my research. It is really important to fund research, and way more than this, I want to say that interdisciplinary research is not only really impactful, but it's really a source of knowledge that then can be spread into many different places. So this is really important, and I also want to thank not only my collaborators around the world, but people who have encouraged me to pursue problems in fusion and plasma physics, and also all the people who helped me prepare this presentation. Thank you all. And before I leave you, I want you to have a closer idea of what does a mathematician's work look like. So if you allow me just 2 more minutes, I just want to tell you a little bit more about this. So on the top left here, you have something that is called the cold plasma model. This is a partial differential equation. It is a different version of Maxwell's equation, and it was derived using a fluid model for the plasma and the coupling between the plasma and the electromagnetic field. This model is what brought me into fusion in the first place during my PhD. That's one thing. Second thing, you have an algorithm on the left here. This algorithm is something that is going to be submitted for publication very soon with one of my collaborators, Ilaria, who's right here. And what this algorithm is doing is to build some particular solutions to Maxwell's equations. So this is very close to what we talked about tonight. And this entire algorithm relies on a particular decomposition of magnetic fields, which is not exactly the one that you've seen, because the one we've talked about was on surfaces with a hole. This one is a different type of decomposition, but still of vector fields. And so at the bottom right, you have here the favorite, the favorite toy of mathematicians, a theorem that tells you how a particular type of field can be decomposed into 3 components. And the H tilde K component, the last one, is the harmonic component that I described earlier. So thank you very much for your attention.
So let's marvel at the beauty of this concluding slide. Mathematics is everywhere. It's in everything. And I think Lise-Marie did a fabulous job of showing the enthusiasm behind the work that math helps us achieve in solving these grand challenges. Doesn't it just make you all want to go back and do more math and encourage your kids and your grandkids to go study math? We really need that future in mathematics. So let's just give Lise-Marie for a round of applause for her great lecture. So remember to pick up your scientist trading cards on the way out, and maybe I'll see you at the basketball game tomorrow where our scientists will be featured on the court. And I just also want to thank you for being here with us. I'd like to invite you to next Wednesday's lecture. It's the last and 4th lecture in the series, which is featuring Dr. Laura Condon from the Department of Hydrology and Atmospheric Sciences. And Laura's going to share a little bit about the talk she's going to give next Wednesday.
Hi, my name is Laura Condon, and I hope you'll join us next week at Centennial Hall for the final lecture in the 2026 lecture series. Human curiosity for millennia has driven us to explore the mysteries of our blue planet and its place in the cosmos. Science is the way we build human understanding across generations and around the globe. It's the bedrock of modern society. In this talk, we'll be exploring how we came to understand our blue planet so far and the role that artificial intelligence can play in the future. Will AI render human investigation obsolete? Join us next week to find out.
For those of you who want to learn a little bit more about stellarators and the mathematics behind them, we're going to ask Lise-Marie to come up and answer questions over here in the corner. But I hope you all get home safe, and thank you again for being here. We'll see you next week.